Welcome to tutorial 2. Today we're going to cover set building. So we've looked at Venn diagrams and we've seen that we represent the universe of consideration as a rectangle, and inside of it we consider different sets. So our universe is on the outside, and then we've got our sets, set A and set B. And if we look at the elements that are housed within each of those ovals, we can see that within set A, we've got all of the negative numbers, negative 3/15, negative 4/5, negative 75.94, any negative number that can be, that is rational, because the universe of consideration for us is the set of rational numbers. And then in our set B, we've got all of the integers. So those numbers 42, 0, negative 31, all of the negative number integers, all of the positive integers, and 0. And we can see that some of these overlap. The negative integers can be represented as negative rational numbers. So they're negative numbers within the realm of all rational numbers. And so we have means of describing this using the Venn diagram, where everything in the pink here are those elements that are in our set A but not in our set B. Everything in the pale blue are elements in set B that aren't in set A. And then we've got those pieces that overlap. So those were those, in our previous example, those negative integers that can also be represented as rational numbers. Outside of all of those are those elements that are still in our universe of consideration. So for us, it was those numbers that were rational numbers that weren't negative and were not integers. So they were in neither set A or set B. And we have a way to represent all of that. So U we'll use to represent our universe. And the elements that are in A but not B, that's our A minus B. No surprise, everything in B that's not in A is denoted B minus A. And the elements that are in both A and B, so in that intersection point, the overlap between our two sets is the intersection of A and B. And then finally we've got, if we look at the union, all of the elements that are in either A or B or both, this is considered the union of A and B, and we're going to talk about what that looks like. And finally, if we wanted to discuss and have a way of describing those elements that are in neither of sets A and B but are still within our universe, we can do that by making use of what we already have. So either you're in the union of what is held within sets A or B, or you are outside of that but still in the universe. The elements that are in U, but they're not in A union B. And so we can use that representation that we saw before. So let's talk about what that looks like and how we build sets from other sets. The first definition is the set complement. And the set complement is everything still within the universe, but outside of our set. So it's the set of all elements not contained within the set A. So if elements in A are represented by that oval in the middle, it's everything outside of that in orange. So it's everything out here. And formally, what that we denote this as a tilde A, and we represent that using set abstraction notation as all of those elements in U such that X is not equal to A. So let's look at an example of that. If we set our universe to be the integers 1 through 9, right here, and we set A to be all X and U such that X mod 2 equals 0, first we have to figure out, well, what's held in A, because that's set abstraction notation. Our universe is very small and finite, so we should be able to list those. And in fact, we know that X mod 2 equals 0 is the same as 2 divides X. right? So it's a multiple of 2. And so within our universe, that means just the numbers 2, 4, 6, and 8. The other odd numbers aren't, 2 does not divide them evenly. Okay, so if we look at the complement then, it's the same as looking at our universe. So our universe is all those numbers. Well, let's make it set A, 2, 4, 6, and 8. And all the other numbers are outside of our set A, 1, 3, 5, 7, and 9. Everything outside of A, that's what's included in, that's the complement of A. And so that's what we get for the complement of A. If we consider the union of 2 sets, on the other hand, this is 2 sets A and B. The union of those 2 sets is denoted as A cup B. So we say A union B. It's the set of all the elements in either A or B. And so we can see from our Venn diagram that's everything shaded in orange. And the formal definition of that is all X in U such that X is in A or X is in B. So it's in one or the other, which means it could be in both, but it's in at least one or the other. So if we look to our example, we're going to start with the same universe. So we're starting with 1 through 9 as our universe of consideration. And then we see that A is set to all the X in U such that X mod 2 equals 0. We've seen that before. So we know that's all the even numbers. And then we see that we have another set. And this time it's all the set in U such that X is prime. So our set B are those prime numbers from within U. So we know that 2 is prime, 3 is prime, 5 is prime, and 7 is prime. So if we want to look at all of the elements in the union of sets A and B, let's just draw it out. We've got our universe U, and we know that we've got the primes in set B. I think it'll be easiest if I draw that first. 2, 3, 5, and 7. This is my set B. And I know that I've got a set A, and I know it contains 2, but it also has 4, 6, and 8 in it. And then outside of that, I see 1 and 9 are hanging around with nowhere to exist. They're in neither A or B. And that's okay. There they are outside in the universe. And so what we're looking for in this case is all of those elements that are in either A or B. So they can be in both, that's okay, but we're going to account for all of them. And in fact, the only elements that are not in that set are 1 and 9. So it's 2, 3, 5, 6, 7, and 8. Let's look at the set difference. So this is a consideration of 2 sets, A and B, and we're going to look at the set difference where we look at all the elements that are contained in the set A, but not in B. So what that means is the order matters here, right? B minus A is not the same as A minus B. And so if we look at our set abstraction notation right here, we see that this is formally defined as all X in our universe, U, such that X is in A, and that's important, and X is not in B. So it's everything in A, and then we have to remove the elements in that overlap. Okay, so let's take a look at some examples. We'll start with the same universe, 1 through 9, and this time we have a new set A. So our set A is defined as all X in the universe such that X mod 2 equals 1. What that means is if I divide X by 2, there's a remainder of 1. So it's all of our odd numbers. And in our universe, that means the numbers 1, 3, 5, 7, and 9. Our new set B is all X in the universe such that X is composite. So it's the numbers greater than 1, the integers greater than 1 in our set, such that the number is not prime, right? So we know in our set it's 2, 3, 5, and 7 are prime numbers, and so our composite numbers are just the remainder. 4, 6, 8, and 9 are composite numbers. So B then is the set 4, 6, 8, and 9. And so if I were to look at the Venn diagram of this, what this looks like is I have my typical universe, and I've got my odd numbers 1, 3, 5, 7, and 9. And then I've got my set B, which I know contains the 9, which also has 4, 6, and 8. And we can see this is our set A and our set B. The only thing that we're going to remove from our set A, we're going to take all of the elements in our set A except those that are in B. And so we're going to remove the 9 because the 9 is in B. So A minus B is then everything in yellow. It's the 1, 3, 5, and 7. The next concept that we want to look at in terms of set building is that intersection. So we can build a new set by looking at the intersection of two sets A and B. And we denote this as A cap B, which we say A intersect B. And it's a set of all elements in both A and B, right? So formally, we say it's all X in our universe such that X is in A and X is in B. It's in both. Where when we use the cup notation, we said the union of A and B, it was in X or X was in B. But this time we're saying it's in both. X is in A and X is in B. And so that takes place in this disk in the middle. So it's those elements that are in that overlap between A and B. Okay, so let's look at an example of this. So we again have our same universe that we started with, 1 through 9, and we have defined our set A to be all those odd numbers, X mod 2 equals 1, 1, 3, 5, 7, and 9. And we've got, again, the same B, 4, 6, 8, and 9. And we remember that Venn diagram looked a bit like this, and we remember 9 was in the middle. We had 1, 3, 5, and 7, and in B we had 4, 6, 8, and 9, and 9 is in that intersection. This time the only thing we want is what's held in that intersection, and so in fact A intersect B is 9. And that's it. So these are some great ways that we can build sets from other sets. For instance, times that we might be interested in the intersect. If I wanted to know those people that lived in Halifax and had an interest in running, those are two sets of people. And if I want to find those people, the people that live in Halifax, where they intersect the group of people that in a social network that are interested in running, that's how I find that group. And so we use this in so many unique and different ways, and we'll explore some of those as we go onward.